All right, ladies and gentlemen, we are going to be calculating the pH of a 0.150 mole per liter solution, okay, of HOOCCOO minus. All right, seems like we've done this before, right? We're probably going to have to make an ice table, write the equilibrium law, because this is probably a weak acid or base. Use the approximation, find X, find the pH. Process doesn't change, but we're getting a little spicier. We went from acid to base, turned up the spiciness. Now we're going from base to, well, it could be an acid or a base. We're actually not sure. And substances that could be either an acid or a base are called amphiprotic, not amphibian, amphiprotic. What does that mean? So amphiprotic essentially means that I could write two possible ionizations. The first one that we should always write is the acid ionization because it's easy and it's already in our data booklets. So let's start with that. Okay, remember we just learned acids donate protons, so it's going to lose one to give us OOCCOO2 minus. It was minus, lost the plus, and H3O plus. And this has a Ka value of, let's check the old data booklet. Flip. There it is. Right here. Whoop. Okay, so these are our two chemicals. This was the acid. This is the base we're producing. Therefore, Ka is 1.5 times 10 to the negative 4. Okay. All right. Now, that's a pretty good Ka value. All right. So it could be, we could work with that. However, we have to confirm that this is going to act like an acid because it could also act like a base. And that's because it has that minus charge. That minus charge means that it could also accept a proton. If it accepts a proton, it's going to become HOOCCOOH, and it's going to produce OH minus. So these are both possible. They could both happen. But what's the Kb value? So we can't use that Ka value that we just used because we don't produce either of these. We don't produce this chemical, or we don't have that chemical. So we need to find somewhere where it contains HOOCCOOH and the anion. And ladies and gentlemen, that's right here. Okay, both of these chemicals are present. That is the Ka value. We want the Kb value. So to do the Kb value, we do Kw divided by Ka, 1.00 times 10 to the negative 14, divided by 5.6 times 10 to the negative 2. Okay, again, we can't use this Ka value because this Ka value refers to both of these chemicals. This chemical is not in my equation, so I need a different Ka, which we found. And guys, Kb is going to be pretty small. It's going to be 1.00 exponent minus 14 divided by 5.6 exponent minus 2. It's going to be 1.785 ... times 10 to the negative 13. All right. So I have two possible reactions, and I have a Ka and a Kb. Which one are we going to choose? Are we going to choose the acid reaction or the base reaction? To do that, we have to compare Ka to Kb. Which value is bigger? Ka, which means Kb will not happen because it's too small. So we're going to erase, or you could just cross it out. I wouldn't recommend erasing it. I have to because I'm running out of room, but I want you guys to just cross out that, and then you're going to be using the Ka reaction. So write both. Underneath the Kb reaction, please rewrite this. I'll give you a chance to do that. Okay, rewrite this, and then we'll get started. Pause this video, rewrite it. Okay, Once you've rewritten it, we're now going to make our ice table. And guys, the problem is identical to what we've already done. Have our ice table, concentration initially of the solution was 0.15. We don't give up about water. We had no products initially. Products are going to go up, obviously. Okay, reactant's going to go down. Boom. So what can we do now? Okay, we have our ice table. We have our Ka value. We can write our equilibrium law. Okay, equilibrium law is Ka is equal to 1.5 times 10 to the negative 4, which is equal to x squared over 0.150 minus x. Okay, we recognize that. We are going to do our approximation to get rid of that. Okay, approximation, take the concentration of the acid, because again, it's an acid. And we're going to divide that by Ka. That's 0.150 divided by 1.5 times 10 to the negative 4. It's equal to 1,000, which is close enough to 1,000. Approximation is going to work. What does the approximation mean again? The old approximation, bud. Sorry, means we can get rid of that minus x. So we can rewrite this as Ka is 1.5 times 10 to the negative 4, which is x squared over 0.150. Okay, again, guys, I hope you are starting to recognize that this procedure is the same as we've always done. And if you were, a betting person or a gambler, which I hope you're not, but if you were, your assignment is going to have a couple questions. One, you're going to be doing this for an acid, you're going to be doing this for a base, and you're going to be doing it for something that is either an acid or a base. Shocker. Okay. Multiply both sides by 0.150. Okay. You're going to get 0.150 times 1.5 times 10 to the negative 4. Square root that gives us x. We remember that x is equal to the concentration of hydronium, because that, oops, that's from this. Okay, so I'm going to do that mathematics. Square root that. I'm going to get 4.474 dot, dot, dot. Don't round it. 10 to the negative 3 moles per liter is my concentration of hydronium. And then bop, do, beep, boop, I'm going to do my pH, step 5. pH is negative log of that, negative log of my answer, and I'm going to get 2.324. I'm going to get 3 decimal places, because my concentration had 3 sig digs. So again, with amphiprotic substances, guys, there's just one extra step. That extra step is determining which ionization you have to use. In this case, we did both. Recognized acid was better, so we used the acid. However, if you had to use the base, you do the exact same process, but instead of using hydronium, you have hydroxide. Okay.